Can you do the Dyson algorithm one?
Sure. So let's look at Dijkstra's algorithm. So here's A, B, G, target graph, E. Copying this from someone's homework, so if this is wrong, you gotta let me know. You're right, okay, good. Is that good? All right, so we're trying to go from A to F. And these start off with tentative distance infinity, so we haven't found a path. This starts off with distance of 0. So find the node closest to the ones that we visited. That looks like B. I'm going to do this without ending up with black all over my hands today. That's my goal. So we've visited A already. There's B, it's a distance of 2. Now we relax all the nodes adjacent to B. So 2 plus 5 is 7, we'll relax our infinity. 2 plus 2 is 4, we'll relax this infinity. And the path to here was A. Okay, now find the node closest to the nodes we visited. And we have another node that's only 2 from our visited nodes. So we'll visit this. The path is AB. And then we relax the nodes adjacent to 4. So this will relax to an 8. 4 plus 1 is 5. This will relax to a 5. And 4 plus 2 is 6. That's already a 2. 4 plus 5 is 9. So that becomes a 9. And now we find the node closest to our visited nodes. And it looks like D, which is a distance 1 from here. So we'll mark this as visited, and our path was A, B, E. And now we relax the nodes adjacent to D. So 5 plus 5 is 10, that's bigger than 2. 5 plus 2 is 7, that's better than 8, so we relax that. And 5 plus 1 is 6, that's bigger than 4, so we leave it. And now pick the node closest, and that's going to be F. So we mark F as visited, and the path was AB, ED.
But if that 2 from D to F was like 5, you can come back to E and go to F from.
Yeah, so is this good for,
Yeah.
right, so that's the solution there. So let's change the problem. Let's say this is 5.
Now, if that one was 5, we first go back to the A to C and relax that one to 3 on the left there.
Yeah, so first of all, this was an 8, right? So that's going to stay an 8.
Wouldn't we relax the A to C right after we did B? Like
Yeah.
B next B,
Well,
we go to B and then the
Oh, we
B
did
is
B,
4
but then this
away.
was a distance of 2.
But isn't it 4 away total?
I think it's the shortest edge to the nodes you visited, not the shortest path to the beginning, because we don't know the length to the beginning. But we know that from the nodes we visited, we can get here with another 2 hops.
No, actually, we showed that it wasn't that a little while ago with the
With
thing
the
that
one.
Ian drew, where it was like a couple steps of 2 on the left side and
Yeah.
a whole bunch of 1s on the right. Remember that graph where we
Oh,
had,
so it's actually the total.
Yeah.
Is that really what we decided?
We did decide that because that's the only way to make that find the shortest path on your left. It
Yeah.
fixes that problem. So in this case, as soon as you hit A to B, or you went to E, then you go back and go A to C.
Go back and go A to C.
Before.
Okay.
Yeah, you always have to reevaluate because you have to keep looking everywhere to find
Right.
if you're eclipsing in length. The
Yeah, okay.
As possible shorter path.
Yeah.
Yeah.
Okay.
I didn't remember that though.
That's not going to change your
It's
your
not.
final answer.
No.
Well, I kind of did that, and I just, I mean, I did for pretty much every combination.
Mm-hmm.
And I had the same answer, but I apparently lost 2 points.
You ended up with
ABE is,
ABED. Yeah, A, B, E, D, F.
Is the shortest.
You're going to F, not to E.
Yeah. We changed stuff just now though.
Well,
Right, yeah.
Like this is not the problem from the
yeah,
from the
but
homework. This
but
changed.
the answer should be A, B, E, D, F, and it should be a length equals 7. And I'm guessing you either had a 4 vertex path or you had a 5 vertex path, and you said the length was 8. They saw both of those. But if it's not there, come up after class and show it to me.
oh.
Okay.
For questions 7 and 8, well, I figured out, but it was triumph, like triumphal. I found that is there any solution to like do this, and you're gonna definitely find that solution.
So what was question 7?
It's asking to find the
Diffusion-Hoover path
yeah.
and
Oh.
diffusion-Hoover circuit.
For a small graph, it's really just trial and error, but sometimes you can sort of figure out. So for Eulers, we know that we have to count number of vertices with an odd degree, right? And if you have something like that, we know right away there's no Euler path because we've got 1, 2, 3, 4 vertices with odd degree.
Okay.
If you only have 2 of these things, so put that there, and let's bring this around. So that's 4, 4, 4, 3, 3. So these are our 2 vertices with odd degree. You can pretty much start at either one, and it's almost solves itself in a kind of fabulous way. So let's just try this. Okay, it doesn't quite solve itself. Huh. 1, 2, 3, 4, 1, 2, 3, 4, 3, 3.
So you do the hardest path ever.
Say what?
So you do the hardest one ever. It's not
I do the hardest one ever. It's
Yeah.
the first time I ever made one up like this.
It's not jumping out.
Yeah. Can I do that again?
Go right, go down, you already went that route.
Oh, this one.
He went down
Doubled up
the side
on that
was
Dang.
Yeah. No, but if you went diagonal at that point, diagonal and then up, left, and then right.
Yeah,
There you go.
there we go.
there you go.
So it's trial and error.
So, the Euler path is where you not visit every edge once, and the
Hamilton is every vertex once.
vertex once.
Yeah,
Only once.
only
And
once.
there's a theorem that says there's no Euler circuit if you have any odd edges,
Right.
correct?
Yeah.
Okay.
So basically, I think if we are going to program something for this, we need to do that with trees. no other solution.
To solve for.
Check if this one works, otherwise.
You
go to
could
the
probably
next,
do
go to the
it
next.
straight with an adjacency matrix. I mean, you can definitely traverse paths through an adjacency matrix. Start at one vertex, pick off the first vertex adjacent to it, go down to that, pick off the first vertex adjacent to it, and you can exhaustively travel all possible paths.
Just single time.
So you still have to do it recursively, you just represent it as adjacent.
You could do it recursively, or you could just iterate. Yeah, recursive is probably easier.
Well,
And you just have to check on each path to see if you've visited an edge more than once. Yeah, it would be a fun program. Maybe I'll do that for program 3 next term. That'd be interesting.
good job, guys. Get harder on the next ones.
Yeah.
As long as it's not on the next ones and not on us.
So,
Oh wait, that's me, isn't it?
How would you, like, so in the next class, data structure, if we're gonna be doing this in Java,
No, data structures is all C.
all C?
Yeah, and then 223 in spring, we do more data structures, we'll be doing in Java.
How do you represent a node then in C? Is it a structure?
Mm-hmm.
Okay.
Yeah.
Struct with probably a name for one of its things, and then what would it be, an array? Second
Yeah, you
name?
could do an array, you could do a linked list, you could take your pick. I believe Java is written in C, so anything you do in Java, you can automatically do in C.
It just may not be easy.
Because you could always write a C Java interpreter and then, but yeah, it may not be easy. But yeah, so 222 is data structures in C. Linked list, trees, hashes, stacks, queues, heaps, good stuff, tries. And then 223 is more focused on object-oriented programming, but we also continue developing data structures, and we redo certain data structures in Java. But we also take advantage of built-in objects, classes for things like trees and lists and stuff. All right, does that help with number 8 also?
yes, thank you.
All right, any other questions on this? Go back to languages and grammars. So suppose we want to represent the language that consists of all strings of zeros, where we have 0 or more strings. So the empty string 0, 0, 0, 0, 0, 0, and so on. Those are the only things in our language. What might a grammar look like for that? And remember, our grammar is vocabulary, terminals, start, rule, and introductions.
Well, we have a starting letter, we have a 0, and every starting letter we can either turn it into a 0, a no, or 0 starting letter again. I mean,
All right, say it again.
that's the null,
Okay, null string.
a 0, or the starting letter and a 0, either before or after, whatever you decided. Did you ever decide?
I didn't find a reason for it, but I'm still gonna.
Enforce it.
No, I'm not gonna force it, but for me, I'm gonna let myself sleep well at night.
I don't think we need that center 0. I think we just.
I don't think we need it either,
Because we can always represent the S with the.
because this S can become a lambda. So I think you only need 2 production rules. It's either the empty string or it's just
But if it's
0 followed by S.
the empty string doesn't necessarily. Did you stick an empty string inside of another string?
No, but we can say,
saying if you make, if you wind up with like 8 zeros and then S, you just make S lambda.
Yeah.
Right.
You're not thinking inside of it, but you're like kind of, you're transforming the S.
Keep getting rid of it.
Yeah.
Right, so our string S could just be lambda, or it could be 0 followed by S, which can be lambda, or 0 followed by S, which could be lambda, or 0 followed by S.
Okay.
You're just picking up
And in this case, our string is lambda. Here our string is, we'll put our strings in blue. Here our string is 0. Here our string is 0, 0, and so on.
So you're just picking up the number of zeros of iterations, basically.
Basically, yeah.
Is there a catch here?
Nope.
The number line.
Okay, now I've got a question for you.
Okay.
What if it was n greater than 0, where you have to have at least one 0?
Okay.
How do you represent that? Can you have conditional grammars?
Let's see.
No, it's only 4.
Well, that's a good question. So,
If you can have a conditional grammar, then for the first character, it could either be, it would be 0 lambda or 0 s. You could say that. And then after that, just go with the same rule. But otherwise, you're left. Oh, I see what you did. That's clever. I like that. That's good. That's good stuff.
does that work for people?
Yeah.
So now our tree comes like this.
And that's how you make a conditional with a binary tree.
Yeah. So, 0A.
It seems so
and
obvious
either
in that.
lambda or 0A.
Should be on in right now.
Right, so that's 0, 0, 0, and so on.
Because lambda's not normal vocabulary.
What is what?
Lambda, what is that?
Lambda's the null string.
Oh, no, it's kind of-
Yeah.
That's fine.
Alright, what about 1 to the n followed by 0, where n is bigger than or equal to 0. So we want to pick up strings
I think
0,
we solved that one actually.
Did we do this one already?
I think we
We did
just
one
solved
similar, but we didn't do this one.
Yeah.
With the technique we just
We have the
used to
technique.
solve it.
Okay. So what would production rules look like? So we'll start from S.
Anybody? We basically just did this with that previous one.
Yeah.
Well, we can start by building out a vocabulary, or just,
Yeah, I'm not going to bother with the vocabulary and terminals
yeah.
unless people want to see them. It's the production rules here that are challenged now. So our sentence can be A followed by 0, and we just want A to be 0 or more ones. And we already did 0 or more zeros. So,
Okay, it can turn into 1A. Or A can turn into
A can be null or it can be 1 followed by an A. That should give us,
Yeah, that should do it.
yeah.
Visualizing that lambda is a null byte, which it isn't.
Right. any string with a number of zeros that's a multiple of 3.
Well, at that point, it's just S.
Let's close it, zeros.
S goes to
Yeah.
3 zeros, followed by an S.
Yep. And iterate.
Yep. Not too bad once you start playing around with it. You actually start to think of things in this way, which can be scary. How do we do it time-wise here? We're in good shape. We'll get to the gushy stuff by Friday.
Just in time for.
Yeah.
This is second element here is going to be have 6 zeros or 9 zeros?
3, 6, 9.
3, 6, 9.
Yeah. All right, so this is one way to describe a grammar. Let me show you a similar way that pops up in languages like compilers and stuff. So Backus-Naur form, BNF.
And what was the first one we covered? Was that phrase structure?
Yeah, it's a phrase structure grammar.
That's what we just studied, is called.
Phrase structure grammars, yeah.
Oh, that's right.
So, I can actually use my laptop for this one. So a BNF is another way to specify a language, but it's arguably a little less quirky than doing these production rules that we've been working with. And by the way, Unix is filled with tools for dealing with all this kind of stuff. You can use things like YAC, YACC, which is yet another compiler, and you can feed it a description of the syntax of a language, and it will create a compiler for you for that language, or something that at least parses the language and tells you if it's valid or not.
I'm wondering if that's how they do a lot of the joke languages.
Yeah. So I had a Swedish chefifier once that would take input and turn it into Swedish chef speak from the Muppets. That was awesome.
It's starting to sound like just a really, really complicated kind of place.
In some sense, yes.
I'm just remembering white space, the joke programming language.
I don't know that
Oh,
one.
God. It's entirely built up of tabs and spaces.
Really?
Yeah.
I mean,
Cool.
that's not so complicated. I mean, I've seen one that's made out of images that's supposed to be abstract art.
Oh, yeah.
But it all compiles down to joke languages like brainfuck or something.
Mm-hmm.
And then you just reuse it from there. You just wrap around it with some binary or something, and you can represent it as long as you get 2 distinct characters. It's
BF is a
not
cool
that
language,
hard.
actually.
And it's not that conceptually difficult once you get your head around it and you've done a little bit of assembly work.
I'm sure that was
Yeah.
physics, but you know.
Yeah.
So here's a description of the syntax of C, written in a form called BNF. Your statements in BNF all take this form, some sort of symbol, colon, colon, equals, and then a list of patterns or replacements that correspond to this, this name over here. And the things you put over here, you can put ors between them to say it could be this, or this, or this. And these can be either more things that are defined elsewhere, or they can be terminal symbols like register, static, etc.
Is that asterisk or regular
I was
expression?
about to ask.
I think that may be a regular expression. I don't normally see that in BNF.
Yeah, because that's only with things that have the curly brace, so
Yeah.
I understand what's the difference.
Inserting.
And you don't need that for a regular
This
expression.
thing looks like it's recursively defined.
It is recursively defined.
Maybe
Which is what makes it fun.
You and recursion.
Is it like a pointer then? But that's C concept and that's not in the.
I don't know what they mean by a star up there, so let me
You've got a plus symbol down here.
let me
which is
show you
also
a simple BNF for an expression that I put together. So, this is going to be an assignment statement. It's a variable followed by an equal sign followed by an expression. An expression is an expression followed by an operator followed by an expression, or it's a parentheses followed by an expression followed by a parentheses, or it's a variable or it's a number. This is very recursive now.
Yeah, fine with
But
that.
if you know what an expression is, you can tell what an assignment statement is. If you know what a variable and an expression are, you can say, do I have a variable, an equal sign, and an expression? So a variable is a letter followed by a variable 2, or it's just a letter. A variable 2 is a symbol followed by a variable 2, or it's just a symbol.
This is really not bad if you got all that recursive.
Yeah. A number is a minus sign followed by an unsigned number, or it's just an unsigned number.
The operators.
An unsigned number is a digit followed by an unsigned, or it's just a digit.
Bingo far.
So when do we start breaking into actual things we can use? Do you still have to define what a letter?
So there's a letter,
Oh, okay, here we go.
there's a digit,
So you have nothing else to define.
Yeah.
Keep going until you can't write anymore.
and
The operator.
I need one more.
It's OP. You have
I
to
also
find
need an
it.
operator.
You have to find what it is.
So a symbol, let me squeeze over here on the side. So a symbol is a letter or a digit or can't read my writing. We'll just call it a letter or a digit. It could be an underscore or things like that. So, or
We'll
an
find out if that
underscore.
breaks things later.
Yeah, right. So an operator plus minus times divide. All right, so what are examples of assignment statements? Well, it's going to be a variable followed by equals, followed by an expression. So a variable could be a letter followed by a variable 2. A letter might be X.
Oh, I see what you did there.
Variable 2 might be a symbol. A symbol could be a digit, and a digit could be a 7. So x7 might represent a variable. This is just an equals sign. And then an expression could be an expression, operator, an expression. Let's just dispense with the operator, let's just make it a plus. But this expression could be a parentheses expression, close paren. So the parentheses are terminal symbols. This expression could be an expression, operator, an expression. This expression, this operator might be another plus. I will make it at times. This expression could be a variable. This expression might be a number. A variable could just be a letter, so we'll just call this W. A number could be an unsigned. An unsigned is a digit, followed by an unsigned. A digit could be 5, and an unsigned could be a digit, and that digit might be a 0. Plus is just a plus. This expression, well, I don't want to do that again. Let's just make this a variable.
Give us a pretty simple for pruning, and we'll go with
Yeah,
that.
right. So this could be a letter followed by a variable 2. The letter could be Q. Variable 2 is a symbol followed by a variable 2. Our symbol could be letter, which is A. And variable 2 could just be a symbol, which could be a digit, which could be a 9. So for this particular parse tree,
X7 equals parentheses W times 50 parentheses plus UK9.
bang, that's an assignment statement.
I prefer this over the previous thing you showed.
Yeah, but
This-
this it'd be a lot more complex to write.
Yeah, this feels a lot more natural to me.
Yeah. Well, because it looks complex, but it's really not.
It's really,
You just keep going until you can't define something by
Yeah.
another definition.
and defining these things, it's really quick to start thinking like that.
Yeah.
Believe it or not. And then processing it, that's the computer's job,
Yeah.
right? So if you describe this in some way that the computer can process, you can take a statement like this and say, is this an assignment statement? And it will simply march down the tree and try to match up pieces of this. And in fact, if it's not an assignment statement, you can usually figure out where the problem is.
Oh, really? So we'll be able to say, like, this part doesn't...
Yeah, so usually, like, if you were missing this number here, if it was W asterisk, right parenthesis, you'll get down to a spot where you're expecting another number, and you won't match any of your patterns, and you can simply see how far you got into your string. Point the finger right there.
And that's why it would throw an error, found, right parentheses, expected, and expression.
Yes,
And that explains syntax errors also.
and that's also why sometimes it's not exactly pointing to the right spot,
Yeah.
So,
but it gets pretty
Because
close.
it doesn't know what you're trying to do, but it can tell what you missed.
Yeah.
That makes sense.
for just future reference, is there a program that prints out trees? And also, is there a print shop that can print out big paper?
Is there a program that prints trees? I don't know of one, but I'm sure people have written them and published them.
I like where this is
I've seen
going.
one online out there.
Yeah.
Can we find a
Make a forest, put it in front of your yard, a bunch of trees.
Yeah, it's a fun thing to try to do though. And print shops that print big paper, I imagine like FedEx probably does
He knows
that.
it probably good.
It's also big printers in
campus too.
Oh, are there? Cool.
Actually, photo, like camera shops that also do photo printing.
So does
Yeah.
Usually do that for you.
train production on campus will do it for you for pretty cheap.
What do they charge for students?
The same rate that they charge faculty.
Yeah, I never paid it.
You just have to ask, yeah. 20 by 30 would be like, I think, $7, $8.
Cool.
Class field trip.
Yeah, seriously.
I'll look at that and say, didn't he say one sheet of paper and he didn't specify the size?
That's right.
Okay, so how would we use this? thought exercise, I could probably figure it out, but how would we use this to represent one of those silly statements you had us do before, like with all the zeros in a row or something? So would you have,
Oh.
you just say
Yeah.
like, you just give it a name. Yeah, okay, so you have a starting operator, could be OS, or O starting operator,
So let's pick a type of string we want to match. What do you want?
like the first thing we start
Bunch
with.
of zeros, just do something.
Yeah,
You want one or more zeros or zero or more zeros?
Zero more, let's keep it interesting.
one or more is more.
All right.
Is zero my string, or just zero?
If we force it to be either zero my string or zero, it's going to have at least one zero.
Oops, that's
But
right.
we can use lambda in here and say it could be the empty string.
What would we call
How do you?
Yeah,
It's just lambda.
but last I checked, I don't have that on my keyboard. Do you mean like,
Can you alt like 164 or something?
No, it's like
/0.
LAMBDA.
That's what I thought. That's what I was thinking. Was either that or just two double quotes with an empty
Yeah.
bit in the middle. Well, that was easy.
Yeah.
Almost easy.
Yeah, this seems a lot better than the directional. I mean, not better, it just feels like it makes more sense.
Like more intuitive?
Yeah, more intuitive, I guess is the word.
It's almost the exact same thing as a production rule, just written differently.
Yeah, yeah.
So,
It seems more computer sciencey this way.
where'd they get that silly operator? Why don't they just use like double equal sign or something?
For that, I don't know, and I never
That's weird.
remember what it's supposed to do.
Are there other ones that do different things? I can't see why you'd need them.
No, that's the only one I know of.
This is really simple. Is there more to this?
No. That's pretty
But it's
much
like
it.
one of those things where it's really simple, but you can propagate it into a bunch of really complex stuff.
Amazing.
Yeah, it's pretty
Okay,
awesome.
so this we would make our own computer language now.
Yes.
It does.
Yes.
Yes, and I highly recommend doing that.
You could make a syntax checker for an existing one. You'd have to be crazy, and you might want to make it a term project, but
Right.
no,
Well,
it's
this is a
doable.
bash script project, you have to make your own language.
Not bash script. What did you say? Yak?
Bash script.
Yeah, Yak will do it for you. But it's much more fun to do it by
So let
yourself.
me guess. You take Yak, you feed it one of these files, and you feed it an example file, and it will tell you if it matched and if it broke or not.
Yeah. I've never actually used Yak. I mean, I've never written anything in it myself.
That seems
So-
like an intuitive use.
You said it's a lot more fun to do it yourself. What do you mean? What would you take the BNF form file and do to it if you're not going to use something like
Make up your own language. Make a compiler for it. Right? Pick a language that only does like 3 or 4 things. Design it however you like.
Right, but that's what I'm saying. Once you design it in this BNF form, then what do you do with that information to?
I can show you what I do with it.
Can you use this BNF form to convert things? Like where it matches, say AS, it would swap it out for
You can
something
do a
else?
lot with this. You can parse to check syntax, but you can also do evaluation with this. For example, the way I've written an expression, I can actually do computation of expression values while I'm parsing. So you can actually get a little deeper into your compilation.
So you're trying to like, could you convert C to Java or something like that?
C to assembly, but you could probably potentially do it to Java too,
Yeah.
if it allows you that level of
Yeah.
control, which I think it does.
Um,
Seems
Go
like
for it.
Yeah, C to Java is more doable than Java to C. When I first encountered this, I was an undergrad, and it was an assembly language library that could be called on the system that I was using. And I grabbed it and I ripped it and I turned it into some C code. So, and I've carried this around with me ever since. I was like in the 80s.
That's what I was gonna say, and you still have it on
I
you.
still have it, yes, and because it's C, it still works. So here's a program I wrote to parse a simple BNF for an expression. So an expression is a left expression, operator expression, or just a left expression, or minus an expression. So you can have an unary operator. Left expression is a variable, a number, or a parenthesized expression. Your operators variables and numbers. Digit and alpha, I think I had as built-ins. These are terminals. Lambda is a built-in, but everything else you have to specify. And I basically use the macro package from C to define things like init state and transactions. And this is a C version of the BNF, so I'm defining what it means to be a parse. So I need an expression. So basically it's something that I want to match, either a terminal symbol or something else that I've defined. So an expression, and then this can be any C statement. If I don't want to use it, I just put in a 1, because 1 is always true. This is an action to take, and this is another state to go into. So my BNF says, this is not on the test, by the way. My BNF says an expression is a left expression followed by an operator, followed by an expression, or it's a left expression, or it's a minus followed by an expression. So I can find an expression followed by an end of string, or that's, okay, so I'm trying to parse an expression followed by end of string. An expression is either a minus sign followed by a left expression, followed by an expression.
I think that minus sign might be for a negative expression. It's not unary operator.
Yeah, it's like minus x plus y,
Yeah.
or just minus x. So a minus sign followed by an expression, that's this. Or it could be a left expression, and I come down to S5, followed by an operator, or followed by nothing, followed by the end of the string, so that's a left expression. Or a left expression followed by an operator, and S6 says I also need an expression, and in that case, I just bounce out with a success. So that basically codes this. And it's a way that I put together, the inspiration came from pre-existing code, but it's a way that I cobbled together to take lines of BNF and be able to code them up in a C-like structure. And it's based on the idea of states. So my state for parsing an expression could be a left expression followed by an S5, and S5 being an operator followed by an S6, and S6 being another expression. So that's left expression, operator, expression. Or an expression could be a left expression followed by an S5, where S5 is just the empty string. That matches this. And so you write all of this BNF, and like I say, digits, alphas are built in, right? So if it's just a tran, it's a built-in thing. If it's an S-tran, then it's a recursive definition. And then my parser basically said, get a line from standard in, take off the new line at the end, call parse on that buffer. If it returns something non-zero, I got an error, so look how far I got into the string. That's what max string is. You can add a caret there. Otherwise, call dump, which does nothing here. And 2 plus 3 minus parentheses 5 times 6. That parses successfully. 2 plus 3 minus 5 times plus 12. And that throws an error.
At the wrong spot.
At the wrong spot, but that's okay.
The really, really, really wrong spot.
There we go. I had an up arrow in the beginning. That's why I messed up before.
Oh, you had to get another character.
Yeah.
Oh.
Bless you. So nothing magic going on here. It's just an option,
But it's pretty cool.
and it's all just this .h file that you have to include that basically defines a few macros to say how to do transitions and stuff like that.
Yes, I was about to ask, what's up with the tran and the state and all that stuff? That's all in this parse.h file?
Yeah, those are defined in here. So tran is a symbol, it's a macro. If you say tran parentheses, 4 things with commas in between, it replaces it with all of this code, which goes on and on and on.
Okay.
And it's basically using a stack to handle the recursive traveling through the parse tree.
Will you be posting this online?
I could post it. I've never posted it before.
I've never shared this.
But I've gotten plenty of joy out of it. Yeah, 1985. Appreciate it. Yeah, I can post that.
And how easy would you say it'd be to translate this to Java?
The parser.
How much
There-
time do you have?
There are probably far better versions out there on Java, certainly, probably even on C. But it uses a C preprocessor, and you can use that with Java code as well. It's really just sort of a pre-treatment of your file. All right, so this takes us dangerously close to state machines. That's where we'll start on Thursday. We'll look at state machines, and that'll take us to Turing machines, and that's what we'll finish with on Friday.